Morning, participants. We are back, and I have the presenter presenting from our cabin. So, may I first welcome the participant, Mr. Gunasilan. Mr. Gunasilan is working as a senior project engineer in PhD TIFAC core in product design. He completed his mechanical engineering degree in Hindustan Engineering College, Coimbatore, and his postgraduate degree in industrial metallurgy at PhD College of Technology, Coimbatore. He worked as a Government of India trainee at PhD Industrial Institute. He also worked as a senior research fellow under IGCA sponsored project titled Experimental and Numerical Investigation of Roof Slab for Future Fast Breeder Reactor at PhD College of Technology, Coimbatore. He is having more than 10 years of experience in design, analysis, additive manufacturing, and re-engineering technologies. He is involved in various projects in new product design and proto-model development activities. He is involved in biomedical modeling projects for various hospitals, and he also works on various students' research projects. Currently, he is working as a senior project engineer in PhD TIFAC core in product design. May I now transfer the controls to Mr. Gunasilan. He'll be presenting this session now.
Thanks for your kind introduction, ma'am. First of all, I would like to thank Mr. Prabharan sir and Dr. Vinod sir for giving me this opportunity to give a presentation about the optical measurement technologies 3D scanner. Straight away we go to the presentation. Currently, I am working as senior project engineer at PhD Type Center. This center was established at the year of 2001. The main objective of this center is to support the industries for the new product design and development activities. This center has full-fledged 3D printing, re-engineering, and vacuum casting facilities. And also, we are conducting workshops, seminars, and short-term courses to the engineering graduates and students from various industries. We are giving service to the industries, more than 100 industries, and also government bodies like ISRO, VSSC, HAL, DRDO, DRL, something. Facilities available at PhD Type Center. Here we have full-fledged 3D printing and re-engineering and vacuum casting facilities. For the rapid prototyping, it's nothing but a condition of 3D into physical product. It's achieved by a layer additive manufacturing technology. This additive manufacturing technology, we have three major technologies called stereolithography apparatus, fused deposition mold, and selective laser sintering technology. Yesterday, Sridhar sir took a presentation about the additive manufacturing technology. So, from this 3D printing technology, we have four major machines. One is stereolithography apparatus machine called Viper SI2 from the manufacturer of 3D System Germany. The machine platform size is 250 mm cubic. From this machine, we can build ABS and polycarbonate plastic materials. And we have one more machine called fused deposition molding machine. This build dimension of this machine is 910 mm, 660 mm by 910 mm. Up to 1 cubic meter part we can build with this machine. 5 material options are available. ABS plastic, polycarbonate, ABS, item and TPSF. These item and TPSF are high temperature withstand material. Maximum can withstand 180 to 200 degrees Celsius. Mostly useful for the aerospace and defense sector. And we have one more machine, selective laser sintering machine. The machine name is called Station 2500 plus. The machine manufactured from 3D System Germany. From this machine, we can build a nylon output and equivalent to stainless steel material for output. We can build the machine. We have one more bigger kind of SLA machine called I650 Pro. The maximum build dimension of this machine is 650 by 650 by 400 mm. Here we are using watershed XC11122 resin, which is equal to the polycarbonate material. For the re-engineering, we are having one advanced level of scanner called GOM RS 2M scanner. It's a blue light technology scanner. It's from Germany, GOM company. Louder, you can speak a bit louder. The vacuum casting technology, we have MK technology Germany machine. So it's useful for minimum job production called sometimes the customer needs 25 numbers, 50 numbers or 100 numbers. Only for that kind of minimum job production, instead of going to the injection molding, it's a very time consuming and very cost effective process. So by using this vacuum casting technology, we can produce a silicon rubber mold output. By using this silicon rubber mold, we can produce a number of duplicates from the single mold. So by using single mold, we can produce 22, 25 number of outputs. Okay. Scanning, the reverse engineering process. For the additive manufacturing or 3D printing, it's nothing but the conversion of 3D CAD model into physical products. But this scanner or re-engineering or reverse engineering process is nothing but the conversion of physical object into 3D CAD file. That is the main thing. So conversion of physical object into 3D CAD file with help of the 3D scanning process. This scanning is nothing but a gathering of undefined 3D-dimensional surface of the scanned object. So many companies are nowadays using this scanner for using this purpose to create a capture the lost design, and in case the customer want to increase their efficiency of the product, or as the developers they want to change the update the existing product, they scan the entire component, get the point cloud data. From the point cloud data to develop the model, then they'll optimize the design for, then they'll enter into the market once again. That is the main thing. Many industries are using this scanner mainly for it's highly useful for tool and die industries and plastic mold industries and aerospace and medical industries are highly using this facility to develop the 3D CAD model. So with help of the 3D scanning process. This 3D scanning classified into two methods. One is a contact method, another one is a non-contact method. This contact method is nothing but a CMM machine. So here we have a touch probe ruby rod. So this touch probe will move over the part, then we'll get a point cloud data. From the point cloud data to we can develop the from the point cloud data, we'll take a sections and draw the curves. Then by using this curve to develop the 3D CAD model. It's a time consuming. So the technology, after the technology development happens, then this non-contact scanners develop in the web. So here, this non-contact method, we have some more classification. One is a structural light scanner, 3D scanner. It may be either white light or blue light. This technology works on the principle of triangulation principle. It's a projecting pattern of the light on the object to scan, then we'll get the point cloud data over the part. So here we have two parts. One is a projector, another one is it's a two camera and one projector system. We know the distance between the one projector and the camera, and we know the distance between object to the projector. So only thing is to measure the triangulation angle and the object to the scanner head. This camera will act as a sensor head. So the projector will project a series of pattern on the object. Then the camera will calculate the distance from the every point in the field of view. Then we'll get the point cloud data. Point cloud data field of view. This structural light either may be white light or blue light. Mostly the white light scanner has some drawbacks in 3D scanning process because the ambient light distraction will be there in the white light scanning process. So it will not that much accurate one compared with the blue light technology. So we bought a blue light technology scanner machine. So it will give the good accurate data and it eliminates the noise. So finally we get a good quality output from the 3D scanning process. Next one is this laser scanner process. Laser scanner. So instead of projecting the series of patterns on the object, it will project the laser point or laser line on the object, then get the reflection from the object. The sensor will capture the 2D data. This 2D data, by using the software, it will convert into 3D point cloud data. So this laser source, the same kind of only. We know the distance between the laser source and the camera head, and we know the distance between laser source and the object. So we will calculate the triangulation angle and the distance between the scanner, the object to the camera or scanner. The reason for re-engineering. The re-engineering process, it will highly helpful to reduce the product development time. Instead of starts from the scratch or the pencil sketch from 2D drawing and then the process drawing or product drawing, then by using the 3D modeling software to develop the model, then going to the process, then optimizing, continuously optimizing, finally we get the product. So instead of this, we have the existing product, then we use the scanner to capture all the features in the component, then we get the whole CAD model. By using this CAD model we can optimize the design, we can enhance the productivity by using this 3D scanning. Normally, this hello. Uh, this 3D scanning process helpful to increase the product development. It reduces the product development time, increase the productivity. So sometimes the customer want to build a component. Sometimes the imported machines or component which don't have any drawings, so they'll scan the entire component. They'll get the 3D CAD file. They'll use it for after some time to reproduce the component. Sometimes in some cases the worn out project parts or worn out turbine blades, they'll scan the entire component, then finally they'll repair it the turbine blade or worn out parts something. So they get the 3D CAD file. Next is the difference between the conventional method of measurements and by using this 3D scanning measurement. So it's a conventional method. It's a time-consuming process. It's a very slow process. By using various measuring instruments to get the individual feature dimension, it takes more time-consuming. But by using this 3D scanner, we get the whole of data within an hour or within a minute. So we get a whole point cloud data. By using this method, we can develop the CAD file, then we can measure it. And also it has some limitation. So the complex features, we can't measure all the dimensions by using the conventional method, like curves or organic shapes or bionic shapes. By using this 3D scanner, we can get all the entire data of the component. So we can use it for various purposes. And also it's not the conventional method is not an accurate one, because the human error is involved in this process. So it's not accurate one. But this 3D scanner combined with the 3D measurement software and the modeling software will get a good quality and good accurate output. And also the conventional method has some bottlenecks. It's a time consuming process. Once we spend time to get the whole dimension of the product, then we give it to the engineer. They'll draw the design and produce the 3D CAD file, then go into the processing center, then the product will develop. So by using this 3D scanner, within an hour we'll get a scan data, then one day we will spend to develop the 3D CAD file. Next day we produce the product. That is a and also this conversion method, it's inexpensive, it's cost effective. But this 3D scanner has some cost limitation. It's a more costly compared with the conventional one. Earlier we used this touch probe scanner, the machine name called Renisha Cyclone 3D scanner. From 2014 we used this scanner. It's same like a CMO only. The measuring dimension of this scanner is 600 by 400 by 300. So it has some limitation, I explained that. So this kind of scanner, it has some limitation because the limited size only we can measure it. And also the rubber kind of component we can't measure it because the touch probe pressure will act on the component. And also it's very time consuming. For example of 250 diameter impeller, it takes 4 hours time to scan the entire component. But with the help of the 3D light scanner or handy scanner, within half an hour or 1 hour we can get the whole point cloud data of the impeller. So it's time consuming and it has some limitation on it. And also it has some rear probe on the object surface, and also in case the soft corner is there, the ball radius will not direct the sharp corner. So that there's some problem. So that's why the 3D light scanner is used very well to get the whole point cloud data very accurate. The process involved in this re-engineering process. Initially, by using this 3D scanner, we scan the entire component, we get the point cloud data. It has millions of points, millions of points. From the point cloud data, we use the softwares like Geomagic or CATIA or SolidWorks, take the sections on the point cloud data, then we draw the curves over the points. In AutoCAD, we'll pick a 3 points to draw the curve or 2 points to draw the line, the same principle. Like that, we'll draw the entire curve, whatever the feature or whatever the curve we need, we'll draw it. From the by using this software tool, by using this curve to develop the surface model or solid model. Then finally we'll get the whole CAD file of the component. This CAD file we can use it for various kind of purposes, die and mold design purpose, or sand casting pattern development, or design optimization purpose, or simulation purpose, or analysis purpose. Various purpose we can use it. That I'll explain later. Okay. Right now we have this ADAS Compact Scan 2M scanner in our center. It's a high-end scanner machine. This machine is a complete ready-to-scan system and lightweight. It's a 2 camera and 1 processor system. It's a blue light technology, very accurate one. It reduces ampere light resistance, so finally we'll get the good quality output. Okay. The blue light scanner. So instead of using the white light, we are using the blue light scanner because the ampere light distraction we can eliminate that. So we get a good quality output. So from the quality output too, we can develop the 3D thermal by using the software like Geomagic or CATIA. So it's a non-contact method only. It's a 2 camera and 1 processor system. It takes several images on the part by using projecting the fringe pattern on the object. Then by using camera to capture the images, it will calculate the distance. Then this 2D software, the 2D image will convert into 3D point cloud data by using the software. Okay. The advantage of ADAS Compact Scan, it's a lightweight and complete ready to scan and blue light technology. It has some scalable point of view, the scalable field of view. The scalable field of view is nothing but in a single shot we can cover the 250 by 250 area of the component. So in case the component size is more, we will move either we'll rotate the component, or either we can rotate the scanner to get the next shot. So by using the reference point, it automatically club together. Finally, we will get the whole point of data. From this scanner, we can scan it from a single coin to aircraft structure. Also, we can scan it by using this scanner. The minimum size also we can possible, and also the maximum size also is possible in this scanner. The technical details of the ADAS Compact Scan 2M. So it's a 2 megapixel camera, so it's a highly accurate one. And also the measuring area is 35 into 30. The minimum size also is possible by changing the lens, and also the maximum size also possible, 1000 into 750 mm². The point spacing is very minimal, so the very dense point cloud we can get it. So we get a good quality, good accurate one output we can get it. And also we can use it for any kind of environment from 5 to 40 degrees Celsius environment, we can use it. The principle of scanning. The principle of scanning is like that. So the series, initially we are normally taken to the scanning process. Initially we fix the reference marker. The reference marker is nothing but a diametrical shape, circular shape stickers only. It's a black and white combination. It's fixed on the component, not series of manner. It's in zigzag manner. So we patch it on the component. Then after that we take it to the 3D scanning process. The series of fringe patterns are projected on the component. So this 2 camera will capture the images. This high-end PCB software will calculate this 2D image into 3D point cloud data. So this special markers will act as a reference marker. Automatically it will generate the numbers. Based on the numbers, it automatically club together. By taking number of images, it automatically club together. Finally, we'll get the whole point cloud data. The software recognizes these markers as a master reference for in case if you are scanning the top direction, top portion of the component, the next time we are scanning the bottom portion of the component, this master reference will act as useful to merge two point cloud data from top and bottom. We can easily alignment together. Then finally, we get the whole point cloud data. By the way, we can get the whole point cloud data. In case the component has an inner feature or internal feature, we can't get the whole point cloud data. By the time we initially we scan the entire component on the outer dimension, then next time we'll cut the component into two halves. Then we scan the inner portion of the component. Then after that we merge together. Finally, we'll get the whole point cloud data. The use of scan data, by using this 3D scanning process, we can get the whole point cloud data or scan data. It's in a .stl format. This .stl format scan data, we can use it for the various kind of purpose. One is for the dimensional analysis. From the point cloud data, we can take a section and we can draw the curve, then we can measure the dimension. Like in case if you want to measure the cylindrical diameter or the distance to distance, point distance or future distance, whatever it may be, we can measure it from the point cloud data. Next one is the re-engineering process. From the point cloud data to take a sections and draw the curve by using the software to develop a 3D CAD model. That can be used for the tool and die purpose or pattern making purpose or some other additive manufacturing purpose. We can use it for some quality control. The inspection, 3D inspection process. From this point cloud data compared with the original master CAD file, we can get a one-to-one comparison. That I will explain later. The rapid prototyping also possible. By using sometimes the statues have number of features, number of properties. So it can't create with the 3D by using software. It's not possible to create all the CAD profiles. So once scan the entire statues, we'll get the whole point cloud data. This watertight steel point cloud data taken to the 3D printing machine. It's in a steel format. The 3D printing machine needs to input file in a .stl format. So we can input into the 3D printing machine. The next 3D printing machine slice the CAD STL file layer by layer. Then we start bringing from the bottom layer to top layer. Finally, we get the whole point cloud data. Like that, the medical imaging process will happen. The doctors will give the CT scan data. From the CT scan data, also we will extract the STL file format. This STL file format put into the 3D printing machine. It starts bringing from the bottom layer to the top layer. Finally, we get the whole point cloud data. The advantages of ATAL compact scan machine. It's a very fast scanner, fast data vision. Quickly we can scan the component in a faster manner. There is no special pictures required for the scanner. So we can move, either we can rotate the component, we can move the component, either we can rotate the scanner, whatever we can do. And it's a complete ready to scan. From the single equipment, we can scan small object to medium object, and also as well as the larger parts also we can scan by this machine, by this scan. And also integrated inspection software is available in this machine, so we can compare part to part or part to CAD, whatever inspection we can achieve. The scan data of the first measurement. Like this, the fringe pattern is projected on the component. We get a 3D point cloud of this part. So projector will project a series of fringe pattern over the part. Then these two camera will capture the images. This image, 2D image, will convert into 3D point cloud. We'll rotate the camera, we'll rotate the scanner, or we can rotate the component to capture the other side or opposite direction. We can use the reverse engineering workflow. From this 3D scanner, with the help of the 3D scanner, we get the point cloud data like this. The whole point cloud data in accurate manner. So we get the complete data of the 3D component. We can use three methods to develop. We can use it for various kind of purpose. One is This point cloud data, mesh data, straight away we can use it for the simulation purpose, either for the analysis purpose or 3D printing purpose, whatever may be, we can use it for this watertight mesh. So next one is a re-engineering process. From the point cloud data, we will take the sections and draw the curves. From the curve to develop the 3D CAD file. It has a design field, so we can edit in future. So that purpose also we can do it. Next one is automatic surfacing. So it's called auto surfacing. It's a very time consuming process. Quick way we can generate the 3D CAD file in the IPS format or step format, whatever we can do it. But it's not editable because it's auto surfacing method. So the software will generate the surface by using the point cloud data, so we get a patch surface. So it's not a editable one. So we can use it for the simulation purpose or some kind of additive manufacturing purpose. We can use it. It's a time consuming one. These are some of the projects we did in our center for various industries, mainly for the automobile industry. This one is a headlight glass. It's a transparent one. By using this scanner, we scan the entire component, we get the quality output. It's a transparent one. For this kind of transparent one or reflective one, we use the chalk powder spray over the component. Then we fix the reference markers over the part. Then we scan it. Finally, we get the whole point of data like this. But then by using software, we develop a 3D CAD model like that. The headlight reflector component, we'll get the point cloud data like this. Then by using software, generate the 3D CAD file. It's a head base, the reflector like head base. It's a complex one. It nearly 1 hour or 2 hours to take the scanning time. Then after that, develop the 3D CAD file. This is a speedometer base. It's a enclosed, it's a minimum size only. The future dimensions are very less. It's around the pin dimension has 0.2 mm thickness only. By using this scanner, we get this kind of minimum thickness features also possible. We develop the 3D. This is one consumer product, test band. We developed the 3D CAD file from the point like that. It's a T-joint wall. Earlier I mentioned that inner portion also we scan by splitting the component into two halves. Initially we scan the entire component, then after that we split the part into two halves, then we scan the internal portion also. After that we measure the whole part with the help of the software. Then by using software, geometric software, we develop a 3D CAD file. This we can use it for injection molding purpose or pattern development purpose, whatever we can use. For its own chair model, plastic chair model. Like this, we develop the 3D curve. The point cloud data, then draw the sections and draw the curves, taking sections and draw the curves. By using these curves to develop the surface, and then stitching this surface, then develop the 3D CAD file like this. It's a blow molding type, the hand glove type. So you can see that the very minimal features also created by the 3D scanner. The grooves also possible to take. It's a shoe bottom sole die component, the injection molding part. So with the help of the 3D scanner, we scan the entire component. The very minute feature also we got it by using the scanner. It's on machine component, machine cover. It's a 2 meter component. By using this scanner, we scan the entire component. Then from the point of view, we develop the 3D CAD. It's on automobile, four-wheeler car, lower radiator grill. It's around 1.5 meter. By using this scanner, we scan the entire component. Then from the point of data, we develop the 3D CAD. It's Maruti Ertiga rooftop car rooftop panel. So it's around 2 meters something. So we scan the entire component, then from the point of data, we develop this 3D. It's automobile steering system for one automobile industry. It's around 2 meter component. We develop it this one. Next application is a 3D surface comparison. Nowadays, these 3D scanners are highly helpful for the 3D inspection purpose. Instead of using the CMM, the CMM is accurate one, but it's not. We won't get all the features. This point-to-point measurement only measure only the particular features only. Length page, watt page, tear, wear, the material accumulation, we can't measure with help of the CMM machines. So by using this 3D scanner, we can scan the entire component. We'll get the whole point cloud data. From the point cloud data, we measure the master CAD file. So we measure the deviation of the component. One to one, we can measure it with the help of the color mapping the software. So we can identify where the shrinkage happened, where the warpage happened, where the material accumulation will happen. So we can identify. But with the help of the report, we can change the gating design or change the mold design, change the dimension. So whatever we can use. So with the help of this 3D scanner, we can do that also. So once using the 3D scanner, we'll get the whole point cloud data. This point cloud data will straight away merge with the CAD file, the master CAD file. Then we get an image like this. From the image report, we can get the idea of the shrinkage wattage and also the material accumulation. Normally, it's called first article inspection. In the sand casting industry, the mold maker, they'll design the runner, riser, grading design on the component. They'll pour the liquid metal inside. So finally, the component will come out from the presentation. So after that, we don't know where the shrinkage happened, where the wattage happened. So they'll use this 3D scanner to enter the component. They'll get the whole point of data. They merge with the original CAD file. Straight away, they'll get the complete report of the component, where the shrinkage happened, where the wattage happened, what is the accuracy of the component, where the more material accumulated, where the less material accumulated. So we can get the idea. So it's highly useful in sand casting industry and also in plastic die making industry also. From this, we can measure where the wear and tear of the die happened in the injection molding die. We scan the entire injection molding die. Finally, we get the measure the original CAD file of the injection molding die. We can measure where the tear, wear happened in the injection molding die. From that, we can rectify the problem. So it gives the accurate result of the component. So it eliminates the labor cost, it minimizes the time, and also human error also. It's good quality and good output we can deliver to the market from the help of the 3D scanner. The surface comparison of the plastic parts. So normally after injection molding, we will get what the shrinkage happen in the injection molded parts. So by using this method, we can identify that defect, then we can rectify that problem. By using a 3-to-1 principle or best fit method to merge with the original CAD file to the point cloud data, finally we get the complete report of the component. And also we can identify the material thickness of inspection available in the 3D inspection software. So we can measure the sink mass and material accumulation of the injection molded parts also we can measure. It's an example what we done it in our center. It's a rapid prototyping output we get it from our center. So it's like one manifold kind of part. So we use this GAM RS 2M scanner to scan the entire camera. We get the whole point cloud data. Then we'll aligned with the original CAD file by using the GAM inspection software. Then we can measure the surface deviation of the component. The green area is a one-to-one area. Then in case the red color area is a more material accumulated in that area. The blue color area is less material available. We can have fringe patterns also. The deviation, we can pick over the component. We can measure the deviation also. How much it will differ from the original CAD file to the point load, we can measure it. We pick the cursor, then we can measure it. Next, sectional analysis also possible. Take the section, then we can measure the internal portion of the profile features also. We can measure by using the GROM inspection software. Sectional analysis also possible. And also material thickness. Where and all the more material accumulates in the component also we can possible in this software. 2D inspection also possible in this software by using the point load data, measure those factors, then taking sections and draw the curves. We can measure the dimension of the part. And also GD&T also possible. Compare with the original CAD file to the part file, then we can measure the GD&T also possible. Cylindricity, circularity, anything we can measure with the help of this software. Some of the work we did in our center. It's on this one for automobile industry. They developed the speedometer panel. It's a speed assembly panel. Then this is the scan data from the 3D scanner. This is the CAD file they gave. Then merge with the original CAD file with the 3D point load data. The surface inspection report like this, they will get it. So based on the report, they will alter the die or something. So where and all the material shrinkage happen, they can have it. It's a cartridge component in the internal part of the speedometer. So it has number of features. This is a scan data of the component. This one is a CAD data they gave, the customer gave. Then merge with the original CAD file with the point load data. Finally, the deviation mapping we can identify. We can pick all the components, then we can measure the deviation. You can see that the 0.5 mm deviation also got in our component. This is one of the components. Then CAD data and CAD data. The merging with the CAD data. The most shrinkage happening in this component. It's a enclosed bag for the speedometer panel. Scan data and CAD data merging with the original CAD file and point load data. Finally, we got the 3D inspection like this. So we pick out the component, then identify the deviation of the component. The output component we can measure. Nowadays, the automobile industries are highly using this 3D scanner. They are merged with the robotic arm. Straight away, the batch production comes. The robotic arm will scan the entire component, various position. It automatically merges with the original CAD file. Then another 10 to 15 minutes, we get the complete inspection report of the component in a series manner. So we can identify quickly where the problem happened, what is the problem, then quickly they will rectify it, then they will accept the component. It's a front dial component, it's a transparent one. So we get the whole point load data like this, then the CAD data, then merge with the original CAD file and the point load data. Finally, we get the measurement complete inspection report like this. The more deviation happened in this component. So like this, the 0.2 mm deviation also we got it. One small video about the GAM scanner. It's a GAM 2M scanner. So by using the picture, for the series of production, they use the picture. They scan the entire component. It's a bigger size of sand casting pattern. The series of fringe patterns protected over the component, then they get the point of data like this. The material color, it's not a matter for this component. And whatever the component, we can measure. Whatever material, we can measure. With help of the reference markers, we can measure the point load data. So So finally we get the whole point of data like this. Then merge with the original CAD file, we'll get the scan report like this. Based on the report, they'll alter the design or parameter something. So finally we'll get a good quality out. Either we can rotate the component or we can rotate the scanner head to get the whole data of the component. By using 2M scanner, we can get the field of view of 200 by 200 area. By using 5M scanner, we can get this area of 500 square mm area. In our center, we have one more scanner also. That is pre-scan X7 handles 3D scanner. So it's a very lightweight scanner. So this scanner we can use it to scan the entire building or the entire car or the entire bus. We can scan the size is not matter of the scanner. It's a four line ray laser scanner. So it's a ray type scanner. So laser scanner. So by using this scanner, we can scan the entire component. The accuracy level is very minimal compared with the GOM scanner. So the GOM scanner is the accuracy level is 10 to 15 microns per meter. For this scanner, we can get the accuracy of 0.03 mm. So for the bigger component, it's highly helpful to scan the entire component in a matter of time. So for the 1 meter component, by using the GOM scanner, it takes so much time, around 2 hours or 3 hours. But using this handheld scanner, we can scan the entire component within half an hour or 1 hour time. We can scan the entire component. That is the main advantage of using this scanner. There are some drawbacks also. The minimum size component is not possible in this component. More than 100 mm or 150 mm part is only possible in this kind of scanner. We can use it in various kind of environment like this. So it's light body and easy operation, easy to use, and high accurate scanner also. So it's highly compatible wherever we can take it. For the on-site purpose, it is highly helpful. For taking this COM scanner, it's not that much easy. By using this scanner, we can use go and take a measurement from on-site industry also. So wherever we can take the scanner, then we'll do the scanning and we'll get the point of data. Then we do the whatever the 3D inspection or 3D modeling, whatever we can do it in our end. The technical details of the pre-scan X7. The measuring accuracy is 0.03 mm only. So and also the resolution is 0.05 mm. The scan speed is more, 4,80,000 scan per second. So the quickly we can scan the entire component within matter of time. So it's a light source is 4 line laser ray. So it's class 2 scanner. So it's eye safe only. We can scan the body also. By using software, we can develop the 3D CAD file. The non-contact method compared with the handheld scanner. So earlier I explained it. This non-contact method is not that much portable. This structural light scanner is not that much portable. So this handheld scanner we can take it in on-site environment also. We can we can take it to the environment, then we can scan it. And also we can scan the entire component with a very big component size for more than 1 meter or 2 meter. By using this handle scanner, we can scan the entire component quickly. By using this GOM kind of structural light scanner, it takes more time compared with the handle scanner. And also this handle scanner, no need to fix the spray, give a spray coating for over the component. And also the front marker also sometimes no needed. But in case of structural light scanner, we need to spray the chalkboard spray in the component in case it has a transparent or reflective one. We need to spray it over the component. In handle scanner, it is difficult to get the minor details of the part. So it's a drawback in this component. In case the sharp edges, we may not get it with help of the handle scanner. Okay. The scanning trends. Mainly this 3D scanning they are using for the reverse, mainly they use it for the reverse engineering purpose, reverse engineering or re-engineering purpose. Instead of starting from the scan or blank slate, we use the scanner to scan the entire component. We get the whole point of data, then quickly we can develop the 3D CAD file. From the 3D CAD file into we can modify the design or edit the design, or we can use optimize the design to enhance our product performance. Like that, in case the pump industry they come up with the impellers, we scan the entire impeller, then we produce the CAD data of the impeller within 1 day or half an hour, half day. So next year onwards they'll start working on the 3D CAD file. They'll minimize the design, or they'll change the van angle, they'll change the height, or they'll change the thickness or something in the CAD file. Then they'll do the analysis work in that 3D CAD file. Then finally they'll actually improve the efficiency. Then they'll go with the constantly they'll go with the product development process. So to quickly we will eliminate the product development time, then we can improve the quality of the product also. We can enhance the performance also with help of the 3D scanner. And computer aided inspection is highly useful in sand casting industry and plastic injection molding industry. With help of this scanner, we compare with one-to-one CAD model. We get the highly accurate inspected data. With help of using the CMM, we only get the future-to-future measurement, or only point-to-point measurement only we will get it. The shrinkage, wattage, and the material thickness accumulation, sink mark, we won't get it. With help of this 3D scanner, we scan the entire component, we get the whole point cloud data. With help of this point cloud data, we can compare with the original pattern, then we get the inspection report. From the inspection report, we can alter the grading design or plastic injection point or something. We'll alter it, then we get the quality output from the with help of this 3D scanner. And also it reduces the cost of the product development. Okay. It saves labor something. Thank you all.
Participants, if you have any questions. Yeah, there is one question in the chat. So can you see in the chat?
And you have a CD scan of 3D object done in G7. Possibly use really rare for 3D. It's always appreciated. Taking the 3D finally coming. The question from Venkata Ramamohan sir. Sir, from CT scan data, the CT scan data is a DICOM image only. So this DICOM image is a layer by layer image only. We can stack it with help of the softwares like 3D Doctor or Mimics kind of biomedical modeling software. Then we'll stack together, then we can extract whatever portion we needed. With help of the density value, we can extract whatever portion we needed. So that we can export that model into .stl format. That .stl file we can input into the 3D printing machine. We can print layer by layer. Finally, we'll get the physical prototype. That is possible with help of the software. The software called easily available is 3D Doctor software or Mimic software. That we can use it. By using this 3D scanner also, Sometimes the customer won't accept to cut the part into two off or three off. They won't allow to cut the entire component. That time, the customer will do the CT scan of the metal part layer by layer. It's a highly costly one. The cost of the machine itself around 8 or something. So it takes layer by layer image. Finally, the stack together. Then finally, we'll get the CAD file, the output in a .stl format. That .stl format also we can take into the geometric software or CATIA software or SolidWorks software. Then taking sections and draw the curves. Then we develop the 3D CAD file. That is also possible with the help of the CD scanner. Any questions, sir?
Participants, if you have any questions, please do voice them.
Yes, one question. Any freeware to edit STL file? STL file, we have like, normally we are using Geomagic Design software. And this, we have CATIA, SolidWorks, whatever the modeling software we can use it. And also the freeware edit STL file like Fusion 360, Autodesk, we can use that software also. We can edit the STL file. That is not it. But quick way we can produce a point cloud data into 3D CAD file. We can use geometric software that can be used very well. So it has a number of features and it's very user friendly. So we can quickly generate the 3D CAD file from the .stl file. Participants, do you have any further questions? Mr. Anbu, do you have anything? So is it okay if we can conclude this session? Thank you, participants. Thank you, Mr. Venkat Ramamohan. I suppose this session has given you some ideas on the topic related, and you have taken valuable input from Mr. Gunasilan. So, with these few words, I think I should thank Mr. Gunasilan for having done a wonderful job of presenting the topic of today's discussion. Thank you, Mr. Gunasilan. Thank you for your time. Thank you, madam. Thank you all for all the participants. Thank you very much. Sir, we will meet at 2 o'clock. The next session will be at 2 o'clock, and I want you to join 5 minutes early.